Section 4.7 is another application of the derivative, where we will be solving word problem applications with the use of the maximization and minimization techniques we've been studying, to solve problems which are called optimization problems. That would mean that we are trying to find the optimal value or values to a given situation in an application. Optimal values could be maximum values or minimum values as the situation prescribes. So for example, suppose that we are in manufacturing and we're trying to package a product, and maybe we want to use the least amount of material that we can in order to package the product. So we can determine, based off of the size of the product and the shape of the product as well, what would be the optimal size packaging in terms of maybe the surface area. So if we wanted to construct a rectangular box or a cylindrical shaped container or something that is conical shaped, so that could be an optimization problem. We are minimizing the amount of material, and perhaps we are also minimizing the cost in production because of the amount of material. If the amount of material is really the only thing for us to be concerned with in terms of cost of the production. Okay, so there can be maximization and minimization problems which can yield optimal values, and we can apply calculus if we can construct, in this course, if we can construct ultimately a single variable equation or function whose output is the quantity we are trying to optimize, and the input can be some variable that we have independent control over, so that we can determine what is the best value of that variable, or values, if the case may be, of that variable of input, so that we get the optimal output value. The equation we construct, which relates the input values to the output value of which we are trying to optimize, that equation we're going to call the objective equation. So for an example where we are trying to minimize the amount of material that we use to package our product, the equation we construct whose output is the amount of material that we create, let's say a surface area equation would work for amount of material for to create a package. The surface area equation I would label as the objective equation, because it's the one that outputs information about our objective for the exercise, the thing that we are trying to optimize. So in many cases, our objective equation will be constructed whereby there is more than one input variable. That is, we will be generally creating objective equations that are multivariable functions. They have more than one input from their domain. So if you take the case of, if we wanted to find the surface area, which is the quantity we would want to minimize when trying to find the minimal amount of material to create a packaging for a product, let's say that we have a rectangular box shaped package and we want to minimize the material in constructing. Well, a rectangular box would have 6 sides. Each of those sides would be rectangular shaped. And most generally speaking, a rectangular box is going to have dimensions length, width, and height. So the volume of such a box would be length times width times height. Okay? And the surface area would be the sum of the surface area would be the sum of the areas of the 6 faces of that box. So you would have a base, which maybe is length times width, but then you'd also have a lid, which is also length times width if the lid is included. And you'd have the 4 sides, and each of the 4 sides you would have either a length times a height or a width times a height. And you'd have to add up the areas of all those sides. And so in any case, the surface area, the total surface area of our package is now defined with respect to the length, the width, and the height, which is 3 input variables for our objective equation, where our objective is to look at the surface area. Now, in order to reduce that objective equation down to a single variable function, which we're going to need to do because in this course we're studying calculus techniques to apply to single input or single variable functions, we would need to have also associated constraint equations. Those would be equations that relate the input variables to each other so that we can reduce our multivariable objective equation down to a single variable objective equation. So some examples of constraints could be telling us that we have how the dimensions are related to each other for our box. Perhaps we're told that there's a square base, and a square base of a rectangular box would imply that the length and the width are equal to each other, or at least two of the dimensions would be equal to each other because it would be shaped like a square. So then instead of length and width and height, we would now have length and height as our three dimensions. So now we can reduce our surface area equation, or volume equation if that's the one that we're using for a different objective. We can reduce it down to two variables now, still a multivariable function. And then if we also had a constraint equation that helps to relate then the other two dimensions, or two other dimensions to each other, if we can relate the length then to the height, for example, we can ultimately reduce our objective equation down to a single variable function. And once it's written as a single variable function where the output of our objective equation is exactly the thing we're trying to optimize, then we can apply the calculus technique. We should check the domain of the function in general. We should be aware of the domain of the function that we're investigating so that we don't end up getting solutions that are outside of what is possible here. Okay, we would not, for our example of length, width, and height, we would not want to get a negative quantity for the length, the width, or the height. Okay, that doesn't mean we wouldn't approach objective and optimization problems where a negative would be okay. There could be cases where a negative is okay. Negative is oftentimes interpreted as an opposite in direction. So it could be a velocity problem, for instance, which could have a negative in it. It could be an altitude problem where negative is indicating, depth maybe below sea level, for example. So there could be reasons why we'd want a negative. But for, if we're talking about surface area and the inputs are dimensions, then the domain would not accept negative quantities. And we would want to consider that. And the calculus techniques we would apply would be based around really the first derivative test and the second derivative test, and essentially the extreme value theorem. Recall the extreme value theorem is that it states that we are guaranteed an absolute maximum and an absolute minimum for a continuous function on a closed interval. Okay. So as a reminder for the EVT, all right, we have a guaranteed absolute max and absolute min, okay, if the function we're interested in is continuous on a closed interval. Now, that does not mean, the EVT doesn't imply that we have to have the differentiability. It's possible that we have a function that is continuous on a closed interval, okay, but it doesn't have to be differentiable everywhere. It could be that the absolute max happens at a point that is a corner or a cusp. It doesn't have to actually be differentiable at that point. Okay, but the extreme value theorem says, well, if we have a continuous function, okay, and it is on a closed interval, it's a single variable function, like we've just been talking about with objective equations we're trying to get to, okay, then we know that the absolute max and absolute min exist. Okay, so the extreme value theorem is, again, an existence theorem. It tells us the thing we're looking for exists. The closed interval method is the technique we use to investigate such a function that is continuous on a closed interval. The closed interval method targets the absolute maximum and the absolute minimum of a function that is continuous on a closed interval by looking at the values of the values that the function outputs at the endpoints and the values that the function outputs at any critical value of the input. And a critical value can be where the derivative is equal to 0 or where the derivative does not exist. Okay, so to take care of cases whereby we might have a function that where the derivative does not necessarily exist somewhere, but we still have continuity, we still would be able to solve optimization problems through the use of the extreme value theorem, because we can still target through critical values. We can target the points for the function whereby the derivative didn't exist. But if the case is that the derivative does exist, then we can use the first derivative test and or the second derivative test in order to investigate the local behavior. Now, for the first derivative test, recall that we're going to be looking at where the critical values are to create subintervals of the domain. So if this line here if that represents our domain, and that domain is not always all real numbers, it's the domain of interest for the exercise. If this represents the domain, then we find the location of the critical values on that domain, where the input variable maybe is x, maybe it's t, maybe it's l for a length, whatever the input is. Okay, so we and test around those critical values using the first derivative. All right, so maybe the first derivative gives us analytical information such that the first derivative is positive within a subinterval or negative within a subinterval, for example. So this tells us about the increasing or decreasing nature of the function. So perhaps it's increasing on this subinterval, and then maybe decreasing on this subinterval, and then maybe decreasing again on this subinterval. And if the function was continuous over this entire domain here, then we would know that we could say that the location of this critical value, that happens at a local max by the first derivative test. So using the first derivative test to investigate increasing and decreasing to determine where we might have a local max or local min. And this point right here is neither a max or a min. Okay, and the second derivative test would require that we are able to find the second derivative on some at least at the critical values. Okay. So we would, using the same critical values, if the second derivative exists at those critical values, we're checking to see what the output of the second derivative might be. Okay. So at the values themselves, not within the subintervals. So if we found that that at this critical value, maybe we had a negative from the second derivative, but maybe at this critical value here, perhaps we output 0. The second derivative at that point was 0. So we ended up with maybe a situation where we had both the first and the second derivative were 0. And if the second derivative is negative at that critical value, that would tell us that the function is concave down through that point at some small interval surrounding that point. And if it's concave down at that point, and that point was a critical value, then that means that critical value is the location of a local maximum. Okay. And if the critical value is, the second derivative at the critical value, if that's equal to 0, then the result from the second derivative test is inconclusive. In which cases, if we get that the second derivative is equal to 0 at a critical value, we would revert to the first derivative test then instead to look at increasing and decreasing. Okay, so here's how we can analyze a single variable function in order to determine where there are maxima or minima. We need to work on creating the objective equations and associated constraint equations as given. Now, constraint equations aren't always just ways of relating input variables to each other, like something like, the length is equal to the width. Sometimes it is some other given information, such as a restriction in the total amount that is available. So, for instance, suppose that we wanted to construct the smallest rectangular box package that we could to package our product. The smallest such package by surface area under a constraint whereby the volume has to be a certain amount, perhaps. So say that the volume of that box was required to be a certain amount. Okay, like say 100 milliliters. We're required to have a volume of 100 milliliters. Okay, or 100 cubic centimeters. Okay, with that restriction, what is the smallest amount of material, the minimum amount of material that would be required in constructing a rectangular box? The volume would then be giving us a constraint. The example I'll give you down here, if we're asked to build the largest rectangular enclosure by area with 300 feet of fencing, well then, the 300 feet of fencing is a constraint. and it yields a constraint equation when we can relate the input variables to each other through this constraint. So to do so, oftentimes we would employ the use of diagrams. Okay, for instance, when it says that the shape is rectangular, I would start by drawing a rectangle and not stop there. I would label the dimensions of that rectangle, specifically in context of what we're trying to analyze with respect to it. Are we interested in the dimensions? Then I want to label the length and the width, which we might call L and W. We might call them X and Y. The exercise itself might even tell us what variables to choose, by the way. We might want to label the area, for instance, or we might be told to subdivide the region into different other regions. Like maybe we want to draw the diagonal of our rectangle in order to create two right triangles for some reason. Or maybe we wanted to draw some parallel sides that are maybe parallel to the width in order to subdivide the rectangle into maybe equal-sized regions, or one region that is twice the area of the other region, or something like that. So I'd want to incorporate this given information as best as possible into diagrams with labels and using variables that are appropriate. Okay, so I like variables that stand for the quantity we're trying to investigate, for example, as an appropriate choice of variable, and not using the same variable to represent multiple things. Like I'm not going to call the length and the width both x, unless I'm told that the length and the width are the same as each other. Right? That's all from algebra, right? Algebraically constructing through the use of geometry, the algebraic symbols, okay, in order to come up with assigning appropriate variables, and then relating those variables to each other, ultimately in an objective equation. And if you can write one objective equation that is a single variable function, so that the output is the thing you're trying to optimize, and you only really needed one input variable, then that's good. And you've either already incorporated the constraints, or maybe there really wasn't much of a constraint to have to consider, or it was sort of built in. But in general, your objective equation can be an equation that has more than one variable. Up here, being asked to build the largest rectangular enclosure by area. So we're asked to find the largest area. We are optimizing area of a rectangle. So we want the area equation for a rectangle. And if we're choosing the length and the width to be the variables L and W, then the objective equation for this example, the objective equation would be the equation A is equal to L times W. Then the output A is the area. That's what we're trying to, in this case, maximize. And the inputs would be L and W. That is a multivariable equation. Now we're going to need the use of the constraint. There are 300 feet of fencing available in order to rewrite our area equation in terms of just one variable. This is how we can do that. Well, 300 feet of fencing, that must be the perimeter of our rectangle. If we can visualize that, we draw our picture of the rectangle, this 300 feet of fencing must be the sum of the side lengths. And we're not being asked to subdivide it or draw a diagonal or create any other fencing on here. It's just the four sides of this particular rectangle. So the perimeter equation, or you can find geometrically from your diagram, 2 lengths plus 2 widths would have to add up to 300. That's a constraint. We are required to use all 300 feet of fencing here. We can't use more and we can't use less, for whatever reason. Okay, by replacing L with 150 minus W, we would now have an area equation where the only input is the width W. So we have A as a function of W. And now we can maximize A, the area, by using our technique from calculus. We now have a single variable function. We should consider the domain. L is greater than 0, W is greater than 0, for example. We may even consider, it may even be wise to consider that, look, we only have 300 feet of fencing total, so we have 2 lengths plus 2 widths. L plus W is 150. Not only are L and W greater than 0, but L and W each must be less than or equal to 150. Right? Because if either L or W was more than 150, then the other one would end up being negative. So in the type notes, I have a few examples here worked out. Not all the details are included, but you should be able to fill in the gaps. I did the main body of work in constructing an objective equation and utilizing constraints in order to get the objective to a single variable equation, and showing you where you can find the answer. Start with this. An open box has a square base and a volume 108 inches cubed. Now, an open box is one that does not have a lid in general. So, whereas a closed box would have 6 sides, it's going to have like 4 walls, a ceiling, and a floor. For a closed box, it would have 6 total sides. An open box would not have a lid. So an open box has 5 sides. Okay, so I've drawn a diagram of a rectangular box here. I've also labeled in here that there's an L and an L down here. There must be further information given. Find the dimensions of the box using the minimal material. What does that mean? Well, the material you use to construct a box would go into its surface area, not its volume. Okay, so we're not filling up the box in this case. Okay, but the volume is instead given to us as a constant. The volume is 108. Now, we are given at the beginning that an open box has a square base, and that's important information. Okay, so the base is going to be a square, so the length and the width are equal to each other. So we can call them by the same variable in this example. So that's a constraint that helps us to reduce the number of variables. Okay, and the height is going to be a different quantity, h, in this case. Okay, find the dimensions of the box using minimal material. Well, then the amount of material is going to go into the surface area, so we need to know what is the surface area of this box. We have 5 sides, and using a diagram here, we have that 4 of these sides, let's call them the 4 walls, the way I have this drawn, 4 of them are rectangles which have dimensions L, H. So L times H is the area of one of these walls, then 4 times L times H would be the areas of the 4 walls together, 4LH. And the base, of which there's only one base because it's an open box, the base down here at the bottom is L times L is L squared. So we have an L squared plus 4LH. Okay. That's the objective equation, because the output surface area is the quantity we're trying to optimize. In this case, we're trying to find its minimum, the smallest such surface area. And the other constraint equation we were given gives us a second equation, because we need to be able to relate L and H to each other through some other relationship so that we can reduce the objective equation down to a single variable function. So we are given that the volume is 108 inches cubed. So volume is length times width times height, which for our square base box would be L times H, so L squared times H. So 108 is L squared times H. There's a constraint. Now we can solve the constraint for either L or H, and it looks like the way it's set up, it would be easier for us to solve this for H, so we wouldn't have to employ a square root. So I'll solve it for H. So H is equal to 108 over L squared. We can then plug that value H into our objective equation, which reduces our objective equation to a single variable equation. L squared plus 432 over L, or 432 L to the negative 1. Now, a further note. In some examples, you could be asked maybe not to minimize the material, or maybe not to maximize volume. It may not be something geometric, but it may be cost. How would you associate a cost with something like this? Well, suppose that we were told that there was a certain cost to producing, maybe for the base, maybe there was one kind of a cost, and maybe another cost for producing the sides. Like, for instance, maybe the base is a little more expensive because it has to be produced out of a sturdier material, just as an example. Maybe the base has to be produced out of metal, but the sides have to be produced out of, wood, or something else, some other kind of material, or just a different thickness of material, or something that's less dense than the base. So if we had a different cost for the base as we did for the walls or the sides, for example, then we could construct a cost function based off of our surface area function. And that cost function would take, whatever the base's area is, L squared is the area of the base, we could multiply that by the cost of the base if we know the cost of the base per square unit of area. In this case, we're given dimensions that are all going to be in inches, right? Because we're given the volume is inches cubed. So the area of the base would be in square inches. Now, if we were told that the base of this box maybe cost something like, 25 cents per square inch to produce, well, then we can multiply the L squared term by 0.25. And that would put our cost function in terms of dollars then. If we multiplied it by 25, we could put the cost function in terms of cents. Similarly, if we're told that the sides maybe would cost 10 cents per square inch, okay, then we can take this 4LH term and multiply that by 0.1 if we're in dollars for the cost, or 10 if we're in cents for the cost. In any case, we can multiply each of our sides by the associated cost per unit area for that side in order to produce a cost function for producing this box. Okay. And then we can still use the volume as a constraint. Ultimately, though, we would be looking at, instead of minimizing surface area in an example such as that, we would be able to minimize the cost. Okay. All right. So to minimize the amount of material asked, what do? We're going to use derivatives. We have a differentiable function on the domain of interest. What is the domain? Well, L and H have to be greater than 0. We can see that L can't equal 0. That would make this undefined anyway. And also, if L was equal to 0, we wouldn't even have a box. It would just be a really tall line. Right? So L and H are greater than 0. And furthermore, they're not going to be so large. Okay, L and H are not going to be so large such that the other quantity would become negative. Okay. All right. So, but otherwise, it is a continuous function, right? This is a rational function. It is continuous on its domain, so it's continuous everywhere except for L is equal to 0, but 0 is not in the domain of the surface area function anyway. So it's continuous everywhere of interest. Furthermore, it's differentiable everywhere we might be interested because, again, it's a rational function. Okay, so we find the first derivative. Why do we find the first derivative? Because we're trying to maximize in this case, or minimize, sorry. We're trying to minimize, right? We're trying to find an optimal value. Find the first derivative. We can set the derivative equal to 0, or see where the derivative doesn't exist. We already said this is differentiable because it's rational, so we're only interested in where the derivative is equal to 0 in this case. Solve for where s prime is equal to 0, so we solve the resulting rational equation. I've done it here. Okay, check the answer to see if that's correct. I have L is equal to 6 inches. Well, that seems reasonable. To make sure that that's in the domain, really, well, let's see, what would be the associated width and height? Well, if L is 6, then the width is also going to be 6. What's the associated height? Go back to the constraint equation. Remember the equation that related L to H directly through the use of the volume? By plugging in 6 into that equation, we can then solve for the resulting height. That would correspond to a length of 6. 108 divided by 36 is equal to 3. So the picture is not to scale. The height of our box would in fact be half of the length of the base. So in fact, the length and the width, which are equal to each other, would be twice as long as the height is. So it's not as tall of a box. And those dimensions, 6 by 6 by 3 inches, those dimensions would minimize the amount of material required to produce this box. That doesn't always guarantee it's going to give us the minimal cost. Remember a moment ago I said, what if the base was more expensive per square inch than the walls? Well, notice that this is going to have a larger base by area than any of the in particular walls. So in fact, we might find different dimensions if we were trying to minimize the cost of such a box. We'd have to investigate the associated cost function in order to find out how that would change. Now, are we sure that this is a minimum? We did find that s prime is equal to 0, and it was only equal to 0 at one point, and that was at one point within the domain. It seems reasonable, but we should verify. Certainly because in general, we could have cases where there's more than one critical value. Right? We want to know for sure, is that a critical value that happens exactly at a minimum, because that's what we were looking for. So in this case, I used the second derivative test. You could use the first derivative test, right? How would the first derivative test look? You have the critical value as L is equal to 6. You have the function, the surface area function is L squared plus 432 over L. So you can test to the left and to the right of 6 in the first derivative. That is, you can test at 5 and you can test at 7 in the first derivative. That's here. Plug in 5, plug in 7, and find the associated increasing or decreasing nature of the function. And because L is equal to 6 turns out to be a minimum, you should find that at 5, S prime of 5 should give you a negative quantity, and S prime of 7 should give you a positive quantity. But you'd have to plug in two values in the first derivative in order to find that. I use the second derivative test here. The cost in the second derivative test is initially taking the derivative. So you take the second derivative, okay, you get this quantity right here, plug in the critical value 6, and the result is a positive quantity. And if the second derivative is positive, it means we're concave up. And since we had a location where the first derivative was equal to 0, it's also concave up, therefore it must be a minimum. Now, the answers to this question were the dimensions, because we were asked to find the dimensions of the box using the minimal material. Suppose that the answer to the question, suppose what we were being asked was not what the dimensions were, but maybe we were being asked how much material would be required as the minimum amount of surface material, right? If we wanted to know the actual amount of material we would need to produce the box, that would minimize the amount of material, we would want to plug our values of L and H back into the surface area equation itself and find out what S is equal to. So we should be mindful of what we're really being asked to report as the answer to the exercise. Are we being asked to report what the input variable values are? And that's what we were asked in this case. What was the length, the width, and the height? Or are we being asked to report what the output would be from the objective? And that can vary by exercise. Okay. So here's a very similar exercise, but also a little bit different. Okay, the geometry here is different. A right circular can, okay, for a stew must contain 36 cubic inches in volume. That's very similar in that we're given a constant volume, and that's going to give us a constraint. The geometry is different, though. Let's draw a picture of a right circular can. Okay, so by right circular, we mean that the base and the height are at a right angle to each other, as opposed to a can that is built at an angle, right? So it's a right angle, the height is at a right angle from the base, and the base is a circle, as opposed to an ellipse, right, or a square. So the base of the can, okay, since it has we'd have to know its radius, the radius is r, then the base of the can has an area of pi r squared. I'm noting over here, I'm drawing the different pieces of our can over here. If we were to take out some shears, and at first if we were to carve off the lid, carve off the base, those are these two circles here, and then if we take some shears and just slice up the side of this can, and then unroll the sides, it would unroll as a rectangle, right? So this gives us a rectangle and two circles. We want to find the radius and the height using the least amount of material. Again, we are trying to minimize the surface area, so we want to know the total area for constructing this can, with the constraint that we have 36 inches cubed in volume. Now, what's the volume of such a can? Well, if we take the area of the circle, the circular base, pi r squared, and multiply it by the height, we get volume. All right? Taking advantage of the fact that this is a right angle here. The volume of this can is pi r squared h. And that must be equal to 36, because we're given that, and that's a constraint. That's going to give us a way to relate h and r to each other. The surface area equation, which tells us the amount of material, would be the sum of the areas of these three geometric shapes. We have 2 pi r squareds. There's 2 pi r squared. And then we have the area of this rectangle. And this rectangle, right, has a height of h, the same height of the can, and the length of this rectangle was exactly equal to the circumference of the base, all right, because we sliced it and we unrolled it. And the circumference of the base would be 2 pi r. So the area of this rectangle is 2 pi r h. So we'll add these areas then together. 2 pi r squared plus 2 pi r h. That's our surface area function. It is a multivariable function. The inputs are r and h. To reduce it to a single variable function, we use the constraint. 36 equals pi r squared h. Let's solve it for h. Okay, so then h is equal to 36 over pi r squared. 36 over pi r squared, plug that in to the objective for h. Right, so we get a 36 over pi r squared. We're going to be able to cancel the pi's. We'll cancel one of the r's as well. Okay, and 36 times 2 gives us 72. So we get this single variable surface area equation with the constraint, the 36 cubic inches of volume, built into our surface area equation already. We built it in through the use of that substitution. And now we can minimize this surface area. What's a reasonable domain, by the way? Well, R would have to be greater than 0. And R can't be anything greater than 0. Eventually, R is going to be so large. Eventually, R would become so large that the height is going to end up having to shrink and ultimately become negative. So we're going to want to make sure that R doesn't become too large. Okay, but let's check and see what the derivatives tell us. Now, we have the first derivative is right here. Set it equal to 0. Solve the resulting rational equation for R. And I get this quantity for R. The cube root of 18 over pi. Verify that is so. Set the first derivative equal to 0. Now, using that value of R, we can go back to the constraint equation and we can find the associated value of H. So H would be approximately 3.58 inches. Okay, so that is going to be the radius and the height, okay, that could potentially optimize the surface area. We have to be sure, is this really a minimum? We can use either the first derivative test or the second derivative test to verify. Okay, our function was written with respect to the variable R. We found R was approximately 1.79. So let's say other values of R that would be reasonable would be like R is equal to 1 and R is equal to 2. We could plug R is equal to 1 into the derivative, the first derivative, and we could plug R is equal to 2 into the first derivative and check to see if the function is decreasing and then increasing. And if it is, and since it's continuous here, as it is continuous since it's a rational function, okay, on that interval, then we would have that this must be the location of a local minimum. Right? It is the overall minimum. If there was another minimum that was reasonable, that is within a domain that we could have, where we could have used another minimum, but if it resulted in a surface area that was even less than this surface area from this, we would want to choose that other one instead, right? We want to get the best of all possible surface areas that we can get. All right? I use the second derivative test here to verify that it is in fact a minimum. Okay? All right, here's a slightly different question involving distance. And I give you this tip here when dealing with distance. If you want to minimize distance or maximize distance even. To minimize distance, well, the distance between 2 points in the rectangular coordinate grid is calculated through the Pythagorean theorem, the distance formula, which is a square root function. And in order to take a derivative of this, you would have to take the derivative of using the chain rule with a square root function and then the derivative of the inner functions as well. Now, the distance between the 2 points is always going to be at a minimum when the square of the distance between the 2 points is at a minimum as well. And this is true because the squaring function, think of y equals x squared, the squaring function is increasing as long as the input is greater than 0. Okay? Now the input is going to be greater than 0 for this squaring function because d is the distance, which is the principal square root, right, by the Pythagorean theorem. It is already a positive quantity. So for an increasing function, and the input increases, then the resulting output increases. Okay, because of that, then we know that the maximum distance would be associated with a maximum square of the distance, and a minimum distance would be associated with the minimum square of the distance as well. So this makes it easier for us to differentiate in general when we're looking at distance functions in our objective equations. Now, the specifics of this particular exercise happens to say what is the minimum vertical distance between these two parabolas. And if it's a vertical distance, then that means that the points of interest are going to have the same x-coordinates. All right, you pick any 2 points. You pick any 2 points on our two curves, like this point right here and this point right here. The vertical distance, right, maybe from here to here, where x is equal to 2. Well, if x is exactly the same, okay, then this difference right here, x2 minus x1, would just be 0. So when we're considering the vertical distance, we're really just taking the square root of the difference in y's squared, which is ultimately just the difference in y's. All right, so if we take the distance, the vertical distance between 2 points on this curve, we want it to be arbitrary points on this curve so that we can let calculus do the work, and we're not just choosing the points to find which are the, what is the minimum distance. Okay, we're going to let calculus do the work. We have the y coordinate for the upper curve here, to have graphed in black, okay, where y is equal to x squared plus 1. and you're subtracting the y-coordinate right from here, the y-coordinate, okay, for the red parabola, x minus x squared was that y-coordinate. Right, again, where the x values are going to be the same as each other, so this is just 0, and the square root of a squared quantity is just going to leave us with that difference right there. So here's our distance formula, and the constraint is already built in. It's already a single variable objective equation. Our objective is to minimize distance. So let's find the minimum. Okay, and the domain here happens to be all real numbers, right? Both of these functions exist for all real numbers. All right, so we can start by simplifying this. So we get x squared minus negative x squared is going to be 2x squared, and then minus x plus 1. 2x squared minus x plus 1. You take the derivative, first derivative, you get 4x minus 1, which is equal to 0 when x equals 1/4. Right? This is a polynomial, so the derivative is going to exist everywhere. It's still possible if we have a function whereby the derivative might not exist, such as in a piecewise case, something like that. We'd also want to investigate points where the derivative doesn't exist as potential critical values. Okay. So x is equal to 1/4. Is this a minimum? Well, it's real easy to find the second derivative here. The second derivative would just be 4. And 4 is always positive no matter what value from the domain that we plug in. Right? For all real numbers, this is positive. So the distance, right, the distance function that we're investigating, we're not looking at the parabolas themselves, we're looking at the distance between these parabolas. Okay, happens to be concave up all throughout the domain. So at x equals 1/4, we therefore must have a minimum. So what is the minimum distance, which is what we were asked to find? Not where is the minimum distance, we were asked what is the minimum distance. So to find that, we go back to our distance formula right here that we constructed for this particular example and plug in the associated value of x, which is 1/4. So calculate 4th squared plus 1 minus the quantity 1/4 minus 1/4 squared. Okay, I have another example here. Kind of a generalized example. With respect to the geometry, find the dimensions of the rectangle of largest area. We want the dimensions that can be inscribed in a circle of radius r. Okay, the objective is to maximize the area of the rectangle. What is the area of a rectangle? A equals L times W. And the constraint here is that we are restricted by the circle itself, right? So the rectangle itself is restricted by the boundary walls of the circle. So let's construct a couple diagrams here. This is fundamentally the diagram that's going to be best suited for this example here. Right, we have the radius. The radius is measured from the center to the edge of a circle, so we can take, for instance, that the radius from the center to the corner of a rectangle. Okay, so we want to find a way to reduce our area equation down to just a single variable. So we need to come up with some way to relate L to W, the length to the width. We'll notice that if we let this extend outward all the way across, right, then we get 2 times the radius. That's one way in which we could look at this. Okay. And then we can create, using this right triangle right here, we have then this side is L, this length is W, and the hypotenuse is 2R. And now we can relate L to W to R through the Pythagorean theorem. So L squared plus W squared is equal to 4R squared. Okay. Now we're ultimately trying to find the dimensions of the rectangle largest area inscribed in a circle with radius r, so we're taking r to be a constant here. We're not told what value r is equal to. R can be any positive value that could be given to us. It's saying that no matter what value of r, that is positive number at least, as long as a positive value of r is given to us, what would be the associated dimensions of the largest rectangle with respect to that r that is given to us. So we're accepting r as if it is already a known constant. So we reduce our objective equation down to a single variable form by solving the constraint for one of our variables, plugging it in. So I've solved it for W and plugged it in to the area equation to get area in terms of L. And then we can go ahead and maximize by the same calculus techniques we've already been using. Okay, and I end up with the result here. Okay, that we have the length is the square root of 2 times r, plugging that back into the constraint equation, to find out what W is. It turns out that W is also going to be the square root of 2 times r. So what we've learned from this is the dimensions of the largest rectangle by area, Okay, the largest area that can be constructed, rectangular area, in a circle of radius r would ultimately be a square. The length and the width would equal each other, and their lengths would be the square root of 2 times whatever quantity r was given to us. Okay, so let's say we take a look at a couple more examples here, okay, worked out fully, maybe from the textbook, okay, or like you would see in your homework. In your homework, you have a couple of tutorial exercises to step you through the process, get you used to it, and then some examples whereby you're not going to have the tutorial steps there as well. Figure out, so it's not going to ask you necessarily for an objective and a constraint equation. That's part of my method to approaching these exercises, but ultimately you want to, here it's asking for an expression for the total area in terms of both x and y. That's something I would call an objective equation. Okay, use the given information to write an equation that relates the variables. That could be considered to be a constraint equation. Okay, the variables here are x and y. They've chosen x and y for this example. They're letting x be the length of each of the two sides with and 3 dividers. Let y denote the length of the other 2 sides. So we might call these length and width, depending on our diagram. They're referring to them as x and y. Okay, what are they doing? Enclosing a rectangular area with 850 feet of fencing. Enclose a rectangular area that is divided into 4 pens with fencing parallel to one side of the rectangle. So you start with a larger rectangle, and then you subdivide that rectangle into 4 pens. Probably don't have to be equal sized pens because you're finding the total area. Okay, now how is that construction in that diagram going to relate to the associated constraint equation that is constructed? So in this example, the constraint is the amount of fencing that is required. But this amount of fencing is not all incorporated into the boundaries, the outer boundaries of the larger rectangle. Some of this fencing is going to need to be used to create, to divide it up into those 4 pens. So you would need, for the lengths and the widths, you would need to determine, well, how many lengths and how many widths are actually required to construct this whole, rectangular region. Okay, and the sum of all those lengths and all those widths would give you a total of 850 feet of fencing. So the example is slightly different than the exercise that was done in the notes. Okay? You read carefully in the instructions and use the variables that they're giving you here. Instead of L and W, use X and Y as they've described. Okay, and then ultimately, so you've written the objective equation, you've written a constraint equation. They're directing you to do that, actually. And then write your objective equation in terms of only the variable x. Notice here they say A equals. They're setting it up so that you can write an equation here with as many input variables as needed, which they give you how many input variables there are, right? X and Y. Not writing it as a single variable function yet. This is in fact a multivariable function here. But here, they're specifically defining that you will be writing this as a function of x down here. So it's only the variable x. And then you can go ahead and apply the calculus technique in order to find the solution. You're finding the largest area. They're not asking you what are the dimensions. So they're not asking you in this case for what is x and y. They're asking you what is the associated area. That would be the largest possible area the farmer could construct. Okay. Let's see, the box with an open top to be constructed from a square piece of cardboard. Consider if you had a flat, square piece of cardboard in front of you. Square, not rectangular, but square. 3 feet wide, so 3 feet by 3 feet square. And then if you went to each of the 4 corners and cut out a small square from those 4 corners, and then folded up the flaps from the sides, you would create a box without a top. Okay? Find the largest volume such a box can have. Draw yourself a good picture of the flat. I would draw the flat square piece of cardboard. I would draw the 4 cut out little squares, of which we don't know how large those squares are yet. And that's where we're going to use a variable. Okay. They say, let x denote the length of the side of the square being cut out. So each of those squares in the corners would have dimensions x by x. Meanwhile, the length of the large square cardboard you're cutting out from, that total length is 3. It's 3 feet by 3 feet. And let y denote the length of the base of the box, that ultimately after you fold up the sides, right, then the length of the base of the box you've constructed, that length would be y. What would be the height of such a box? After you've cut out those little squares and folded up the sides, what would be the associated height, do you think? Write an expression here for the volume of that box in terms of x and y. So what does v equal? There's an objective equation. It is a multivariable equation. Now use the given information to write an equation that relates x and y. What's the constraint here? We're being told that the piece of cardboard must be 3 feet by 3 feet. That's a restriction. And that's going to help us to relate x to y. So come up with your constraint equation. Then combine these into a single variable objective equation where they're saying they want the single variable to be x, and then solve the problem. A couple more here. Okay, storage container. This one has cost associated with it. I mentioned that earlier. Try the cost one out. Here's a different shape, the Norman window. It has a semicircular region on top, so you can take this portion on top as a half of a circle, and then it has a rectangular window down here. Okay, never mind the extra, the extra slats in here. Okay, just imagine that you have a rectangle here, and then you have a semicircular region, what is half of a circle up here as well. They give you the perimeter of the window, that is all the way around. Okay, it does not include these extra bars in here like this. The perimeter is this length, this length, this length, which is a semicircle, and this length. That total perimeter is 24 feet. There's a restriction. Find the value of x, where x is this length down here, so that the greatest possible amount of light is admitted. The amount of light is increased by increasing the area of the window. So they're saying, what is the largest possible area that you could construct if the perimeter is 24 feet? And we still don't know the height of this rectangle here. We should not assume that it's x, because we weren't told that this was a square down here. We were told this was in fact a rectangle down here. Okay, another one about distance. Okay, an application about light intensity and photosynthesis. They're giving you a function. Okay, find the light intensity for what light intensity is P maximum. Okay, and a couple more. All right, a couple more ones involving graphical equations. Okay, in the book. I like this exercise. So if you are offered one slice from a round pizza, in other words, if you're offered a sector of a circle, and the slice must have a perimeter of 32 inches, so the perimeter is supposed to be 32 inches, that's a constraint, okay. What diameter pizza will reward you with the largest slice? Okay, maybe not a practical example, but nonetheless entertaining, I guess. Alright, so let's see. So we have a round pizza, and we're taking a slice of that pizza, which is a circular sector. Alright. The area of a circular sector formula is A is equal to theta over 2r squared. Okay, from trigonometry. If we take that the area, real quick, like where does that formula really come from? Right, if the area of a whole circle is pi r squared, okay, and let's say, and if we say that this is the area if if theta is equal to 2 pi, okay, then we can say that this is the area of a circular region where pi is equal to theta over 2. Alright, so we're dealing with radians here. When we're using this formula, we're dealing with theta is specifically in radians. So in radians, if theta is equal to 2 pi radians, that means we have a full circle. So it's like if we took the area of a sector where the sector was in fact the whole circle, we would get the area of the whole circle, which is pi r squared. So if that's where theta is 2 pi, then pi is equal to theta over 2. Then plug theta over 2 in for pi, and you get theta over 2r squared. Here's our formula for the area of a circular sector. Okay, where theta is this angle right here, measured in radians, r is this length, but is also this length right here. The perimeter of our circular sector is going to be 2r plus this length right here. And that length right there is called an arc length, right? S is the circular arc length. Also from trigonometry. The relationship between arc length and radius and theta is that S is equal to R times theta. In other words, theta, the radian is defined as the ratio of circular arc length to radius. S divided by R will equal theta. If it was the unit circle, where R is equal to 1, if R is equal to 1, then arc length is equal to theta, as long as theta is in radians. And that's where we use T, right? Like for our trigonometric formulas. So S equals R times theta. So we have P is equal to 2R plus R theta. All right, and we're given that 32 inches, this is our constraint. Okay. All right, here we go. Constraint would be that 32 inches is equal to 2R plus R theta. Right? Our objective equation is the area equation. 1/2 theta R squared. Okay, so we have an objective, we have a constraint. All right, I'd like to write them one above the other. Constraint without the units. 32 equals 2R plus R theta then. Okay. Right, and just to check, right, what diameter pizza will reward you with the largest slice? Okay, so we have diameter is equal to 2 times radius. So we want to find out what R is equal to. Okay. All right. So we want to find D is equal to 2R such that A is maximized. So let's write A as a function of R. We can do that by solving for theta. Okay. So the constraint equation, 32 minus 2R, and then divided by R, is equal to theta. Okay. So we have that. And then plugging that into the objective equation, reducing it to single variable form, so we can get A as a function of R. Let's see, that would be 1/2 times theta, where theta is now 32 minus 2R over R, times R squared. There's our objective equation in terms of R. And let's clean this up. Okay, so A of R is equal to, let's see, we can cancel this with one of these R's down, with this R down here with one of these R's right here. We can also factor out a 2 from this numerator to cancel out this 2 right here. Right, so that'll leave us with the quantity 16 minus R times R. Okay, canceling those and canceling a 2 with a factor of 2 from here. And to get ready to take a derivative, it'll be easier, I think, to take the derivative if we expand this. So 16R minus R squared. Okay, now we're going to optimize. A prime of R is equal to 16 minus 2R, and that's equal to 0. Okay, that's equal to 0 if, 16 is equal to 2R, then that's when 8 is equal to R. So area, okay, has a critical value. So this is a critical value right here. R is equal to 8. Let's check to see what kind of what the behavior is at that critical value. I'm going to use the second derivative test. The second derivative of this is -2, and -2 is less than 0 for all r that are in the domain for this function. Okay, and right now we have that r is greater than 0. Okay, at least, right? So if the second derivative is negative, then that means that we are concave down. And if it's concave down, then that means this must be a maximum. Okay, so A, or area, is maximized if R is equal to 8. Okay, and we were given this in inches. The constraint was given to us in inches. If R is equal to 8 inches. Therefore, the area is maximized. We were asked to find the diameter that would maximize it. The area is maximized if D is equal to 16 inches. Okay. So I'm getting 16 inches for the diameter. What diameter pizza will reward you with the largest slice? This is 16 inches. Okay, so let's say we take a look at just one more example here. Take a look at this number 48 right here. Kind of similar in design to what I think looks like a related rate exercise. Here we go. But it's an optimization problem in this case. It says a boat leaves a dock at 2 p.m. and travels due south at a speed of 20 kilometers per hour. Another boat has been heading due east at 15 kilometers per hour and reaches the same dock at 3 p.m. So I need a diagram to visualize this. And then it says at what time. So we're going to need to relate their speeds that they're traveling. We need to relate them to time. Since we have uniform velocities here, these are unchanging speeds, so we can use distance equals rate times time to relate these. Right, to relate a speed to a time through distance. At what time were the two boats closest together? Again, minimizing distance, that's when they're closest. Let's get a diagram together. We have one boat leaving a dock at 2 p.m. traveling south. Another boat which was heading east reaching the dock at 3 p.m. So I'll take this to be the dock. Okay. We have one boat that it said was traveling south from the dock. Okay. I'm going to call this boat one, B1 for boat 1. Okay. And then we had another boat that was that left at 2 o'clock, I guess it was, or it said that it was just traveling east is what it said. It was traveling east, and it reached the dock, right, at 3 p.m. Sorry. There it is. Something like that. Okay, so this is sort of the trajectory that, for boat 2. Okay, so B2. And we want to find out for any time along this journey, at some arbitrary time along this journey, there is going to be the associated distance between the two of them. I'm going to call that D. Okay? So D is going to be the distance, okay, from boat 1 to boat 2. And that can be at time T, ultimately. That's what I want. Okay. Let's see how we can construct it. This is going to be in our objective right here. Our objective. So that then we can minimize that distance. Okay, this gives us a nice right angle here. Okay, because we were told one boat was traveling east and the other was traveling south. And then we were also told their associated, the velocities, right? We were told that boat 1 was traveling south at 20 kilometers per hour, and boat 2 was traveling east at 15 kilometers per hour. All right? 2 p.m. travels due south at 20 kilometers per hour. Another boat has been heading due east at 15 kilometers per hour and reaches the same dock at 3 p.m. Okay, so it has been heading east. So we would presume then that this other boat that was traveling east, was already traveling east at 2 p.m. because it says it has been heading east. So at 2 p.m. it was already moving at 15 kilometers per hour, and it ends up reaching the dock at 3 p.m. So it started, okay, so then I would say that boat 2 was starting 15, not miles, kilometers, right? 15 kilometers to the west of the dock at 2 p.m., right? But boat 2 was exactly at the dock when it hit 3 p.m. Okay, let's let B2 of t be a function of time. Okay, let B of t be the, not just the distance, but the position. Let's let it be the position function for boat 2. Okay, where we have that t is the time since 2 p.m. measured in hours. All right, so this statement here, that it was 15 kilometers west of the dock at 2 p.m. Okay, and the position function, by the way, the position will be relative to the dock, since that's a central point that, you know, to reference for both boats, I think. So if the dock is position, let's say position 0, imagine this on a number line then. If I extend this outward, as this was a number line, then 0 would be where the dock is. A positive quantity would indicate to the east of the dock. A negative quantity would be indicating to the west of the dock by this construction. And then vertically, do the same thing vertically. So that positive position would be north of the dock, negative position would be south of the dock. I think we'll do it that way. Okay, so we have B2 of 0. That's when time since 2 p.m. was 0. That would be at 2 p.m. then, okay? At 2 p.m. the position was negative 15. That would be kilometers, okay? At negative 15 kilometers, the negative means west of dock, and the t equals 0 means 2 p.m., right? All right, t equals 0 means that this is at 2 p.m. So I'm reading this statement as boat 2 at 2 p.m. was 15 kilometers to the west of the dock. And then B2 of 1 is equal to 0 kilometers. I'm reading that statement as saying that boat 2 at 3 p.m. was at the dock. Right? Reading it as boat 2 at 3 p.m. was at the dock. Okay. Similarly, I'm going to construct a function b1 of t. Okay? So we have that b1 of 0, that would be position at 2 o'clock. At 2 p.m., boat 1 was at the dock. Boat 1 at the dock at 2 p.m. And B1 of 1, this boat is traveling at 20 kilometers per hour south, so after 1 hour, it has gone 20 kilometers. So B1 of 1 would be position negative 20 kilometers. Okay, so I'm reading that as boat 1 at 3 p.m. is 20 kilometers south of the dock. Okay, now we can build general functions for these two boat models, right? B2 of t. Okay, it's linear, and it's connecting. All right, it's connecting the points 0, -15, and 1, 0. Right, so this is linear from 0, -15 to 1, 0. Okay. All right, the y-intercept is -15. All right, the b-intercept, right? The y-intercept is -15, and the slope is what? You got y2 minus y1, so that's positive 15 divided by x2 minus x1, so 15. So 15t minus 15. And b1 of t is also linear. It goes through the points 0, 0, and 1, -20. So its y-intercept is 0, and its slope is y2 minus y1 is -20 divided by x2 minus x1, and so it's -20, so -20t. So here's two linear equations. Okay. Now the distance between the two at any given time, when distance as a function of time, we need the distance for boat 2 from the dock at that time, and we need the distance for boat 1 from the dock at that time. Okay, so the distance function between the two boats can be found by squaring, right, the distance from boat 2 from the dock, so that is the position of boat 2 relative to the dock squared, plus the position of boat 1 relative to the dock squared. So you get 15t minus 15 quantity squared plus -20t quantity squared. It's our distance function. Okay, sorry, that's the distance function squared. And we can associate that, okay, all right, with a square function. So we can just call that d, so that we can then minimize the total distance. Okay, just call this d. So d equals this, right? This expression right here now. I'm going to call this 15 times t minus 1 quantity squared plus -20t squared. Okay, so this would be what? 15 squared is 225, and then that's times t minus 1 quantity squared plus 400t squared. Okay, let's take the derivative of that. So d prime of t is 2 times 225 is 450, then that's times t minus 1 by the chain rule is just times 1, and then plus, this is going to be 800t. And let's set that equal to 0. So we have 450t minus 450 plus 800t is equal to 0. So that's what? 1250t is equal to 450. So t equals 450 over 1250. Let's see, divide by 50. We get what? 9 over 25 hours since 2 p.m. 9 divided by 25 is 0.36. 0.36 hours since 2 p.m. Okay. Let's see. We turn that into minutes. All right, 0.36 hours. We have for every 1 hour, there are 60 minutes. So multiplied by 60, we get 21.6 minutes. Okay, and 6/10 of a minute, we have about what, 36 seconds. Okay, so the distance was minimized at 2:21. Okay, 2:21 and 6/10 of a minute, right, was at 36 seconds. Okay, there you go. All right, so that's the time when the distance between the two boats was minimized. Okay, so that's it for this section. Check out the type notes and the homework. Okay, let me know if you have any questions. Take care.